I am Nick Clinton, Earth Engine Developer Relations. It's my job to help you make use of Earth Engine, and this presentation is just a brief introduction. We get the question a lot, why is Google doing this? And this is part of the answer for why is Google building this Earth Engine. There is a whole constellation of satellites out there from a variety of space agencies all over the world, and these satellites and other instruments are constantly collecting data all over the world. The problem is, if you don't have a high bandwidth internet connection, it's hard for you to get these data. And even if you have a high bandwidth internet connection, and you're able to get the data, it's still hard to store all the data. You have to have lots of hard disks. And even if you have a good internet connection and lots of hard disks, you still have to have a powerful computer to analyze and visualize the geospatial data and get your work done. So that makes it hard for many folks all over the world, even at fairly high-level institutions, to make really good use of all the satellite imagery and other geospatial information for the purposes of environmental monitoring. It is Google's mission to organize the world's information and make it universally accessible and useful. So we see Earth Engine as like the geospatial manifestation of this mission statement. We want to organize the world's satellite imagery and other geospatial information and make that universally accessible and useful to you folks. How do you do that? It is much easier to move your question to the data than to move the data to you. So that's the basic idea of Earth Engine, is that first we get all that satellite imagery and pre-process it and host it on Google machines so that you don't have to. So the idea here is that it's much easier for us to provide you with compute infrastructure near the data than it is for us to move the data to you. And so that's really how Earth Engine works. There's this large petabyte of Earth observation data, 17 petabytes and growing. As new scenes come in, it's just a few days time between when the sensor acquires the scene and when it ends up in Earth Engine. There's lots of stuff in this data catalog, so all Landsat that USGS has, we have. So Landsats 1 through 8, not including 6, of course, processed to raw and top of atmosphere reflectance and surface reflectance. Most MODIS terrestrial composites and some ocean composites. All of Sentinels 1, 2, and 3, provided we can get them from Europe. Sometimes there's a delay there, but we have all of Sentinels 1, 2, and 3, or we're getting it. Climate data and weather data, land cover data, a variety of tables and other geospatial data sets. And in order to discover that, you can, of course, search the data catalog, and I'll show you how to do that later. However, all this data is not necessarily useful without compute infrastructure. So co-located with this data archive is Google's massive cluster. So the same cluster that runs things like search and YouTube and Gmail can be used for geospatial processing. So co-located with this data archive is this compute infrastructure. But of course, the compute infrastructure is not necessarily useful to you without an API that lets you implement your geospatial workflows. So we provide 2 APIs, and there are more coming. But for now, most people choose to start with the JavaScript API. And here's the JavaScript API running inside our online IDE, which we call the code editor. So this is just a screenshot of the code editor running inside a Chrome browser. And this is JavaScript. And most people choose to start learning Earth Engine with JavaScript because there's this online code editor and because all our docs are written in JavaScript. And also, it's very easy to learn. But if you prefer to code in Python, there is also a Python API. And it is virtually identical to the JavaScript API, except for syntactic differences between the languages. So the point is, if you learn the JavaScript API in the code editor, you'll automatically know the Python API. So that's just a little bit about the the background of Earth Engine in terms of why Google is doing it. Here's a concrete example. This is a Landsat scene from the southeast coast of Borneo, and this is, at the time this scene was acquired, this was the most cloud-free image of this area. And obviously it is still pretty cloudy. But the thing about these clouds is that they move around over time. So by opportunistically picking patches of clear pixels, by applying a relatively simple algorithm, for example, the median in every pixel, you can turn a year's worth of cloudy imagery like this into one relatively cloud-free image like this. And so again, this is just the median applied in every pixel. Cloud shadows are dark, clouds are bright, and reflectance from the Earth's surface is right in the middle. So this was a hint that Earth Engine was doing something useful. And once you've done this for one little patch of Earth, the next logical thing is to do it for the whole world. So this is a 1-year cloud-free composite from Landsat imagery. And this is not a true representation of the Earth's surface, of course. There's not a cloud in the sky anywhere. It's a greenest pixel composite, so it's springtime everywhere. And this is not a real representation, but it does make for a beautiful visualization. So we called this Pretty Earth internally, and this became the background that you see, the satellite background that you see at specific zoom levels in Google Maps and Google Earth. Once you have done this for the entire world at 30 meters resolution from Landsat for 1 year, the next logical thing is to do it for the whole world at 30 meters resolution for 30 years. And that project became known as time-lapse. Time-lapse is a video or an animation, if you will, of 30 years of Landsat imagery. And this is online. It was initially released on the Time magazine website and won some awards for the best use of video on the internet. And this is what it looks like. I'm just showing you this global animation so that you believe me that this is in fact a global product. But it's more interesting to zoom into some specific locations. And here's an example of that. So this is a river. This is in Peru, in the Amazon forest. And what you can see is this river meandering over time. And here's a little town. This is called Pucallpa, Peru. And what you can see is the river is kind of going towards the town here, and the town is like running away from the river in the other direction. Here's another example from China. This is Suzhou, China. And what you can see is that the city starts in this little place and is initially surrounded by agricultural land. But over 30 years, the city just grows outward into this agricultural land. So you can see urbanization taking place as well. Here's another example. This is from the Brazilian Amazon rainforest, and what you can see here is logging or deforestation happening over time. And the point that I'm making here is that these are very powerful visualizations. And you can go to time-lapse online. This is the link. You can get there from our homepage, earthengine.google.com/timelapse. You can pan, you can zoom, you can interact with this video. You can go to the places of interest, to your places of interest, see change happening right before your eyes, and then try to quantify that change using Earth Engine. So this is a huge job. 30 years of satellite imagery, millions of scenes, millions of hours of computation, trillions of pixels. But when you do this in massive parallel on Google computers, you get a result in days. So this is really the power of Earth Engine. It's like having your own personal supercomputer in order to execute your geospatial workflows. So that's just a little bit of the background of Earth Engine in terms of why Google is interested in this problem and some early internal use cases. But as I mentioned previously, the core of Earth Engine is this online data catalog. And I won't say too much about that now. I just want to show you a picture of how you access that Earth Engine from the code editor. So this is the online code editor running inside a Chrome browser, and I'll give you a short demo of that later. But suffice it to say that there is a search functionality here, and this search functionality is your entry point into the data catalog. So you can enter a search term or a place term here. And so for example, I just entered Landsat Collection 1, and now you find all these collections of imagery, or image collections as we call them. These are data sets that have been preloaded into the data catalog, and you can use directly in your code. So I'll give you a little demonstration of that catalog later, but I just want to explain a little bit about how you use Earth Engine. And as I mentioned previously, most folks choose to start with this online code editor. This is code.earthengine.google.com, and you can sign up for that for free. This is JavaScript in the code editor. Again, most people choose to start by learning JavaScript because there's this nice online IDE, and we have all our docs in JavaScript. That is useful for this interactive mode online, or if you're using node.js, you can also write JavaScript code for Earth Engine JavaScript code for node.js. But if you prefer Python, there is also the Python API, which you can download or install with pip. And the difference is that you don't get this nice online IDE, but you can do things like create web applications on the App Engine framework. So these are web apps powered by Earth Engine, and generally you need to have Earth Engine Python code in order to run an App Engine. If you are a notebook person, you can also run Earth Engine inside a Jupyter notebook, or for example, use Google's version of that for Drive, which is called Colab notebooks. So you can install Earth Engine right into a Colab notebook and use the Python API there. How does this work? The code that you type into the online code editor, or the Python code that you create on your computer, never runs at Google. Instead, it gets turned into a request object. This is a fairly small JSON request object that gets sent to Google servers for processing. When Google receives your request object, the geospatial data sets you ask for are loaded, the algorithms that you request are loaded, and your algorithm is then parallelized over many, many machines, and your computation takes place in parallel on many machines, and all you get back is the result. And that result might be a statistic. It might be a little display tile that you can see in your web browser, for example, a JPEG or a PNG image. But the point that I'm making here is that this is a low bandwidth operation. So you don't need a very powerful internet connection. You also don't run any of this stuff on your machine. All this is happening on Google servers. So you don't need a big hard drive. You don't need a powerful computer in order to make Earth Engine work. That's just some very basic details about how Earth Engine works. There's this great paper by my colleague Noel Gorelick et al., which is open access. And if you want to know more about how Earth Engine works, please see this paper. So that's just a little bit about the background of Earth Engine, and a little bit about the data catalog and the API. There are some concepts here that are important to understand in order to make Earth Engine work. And specifically, if you're coming from a GIS or image processing or remote sensing background, there are some new and different things that are worth discussing here. So first, just data structures. Of course, there are vector data in Earth Engine, and we call vector data in Earth Engine features, and collections of features are called feature collections. Each feature is a geometry, so a point line or a polygon, and a set of attributes, which we call properties. And so you can load, for example, ecoregions, and we have a variety of these tables stored in the data catalog for you to use. Raster data in the Earth Engine are called images, and a stack of images is called an image collection. So a time series, if you will, of images is stored in an image collection. And this is where Earth Engine starts to get a little bit weird, because each band in an image can have its own projection and registration and even resolution. So this is different from your standard image processing software that you may have used in the past. Each image is a collection of bands. Each band is a collection of pixels, and the pixels have a mask and a projection and a resolution, but you also have properties which include the bounding box of the image and other metadata that might be stored with the image. As I mentioned previously, collections of things are called feature collections or image collections. It's just a stack of things that each thing in the stack stores metadata, so you can filter by metadata, you can sort images or features. For example, you could sort features by area or images by cloud cover. You can join collections together. And in order to do things to every element in the collection, you would map a function over them. I'll talk more about that in a second. And then in order to aggregate the collection in some way, spatially or temporally or perhaps spectrally, you would use a reduce operation. And I'll talk about that in a second too. So if you're used to traditional procedural programming, you probably have written a for loop. And that is not how you do a for each operation in Earth Engine. Instead, you use a map operation. And here I'm talking about map in the mathematical sense of applying the same operation to every element in a set. So, for example, if you have an image collection and you want to compute NDVI for each image, you would map a function over this collection. Or if you want to compute the area of each feature, you would map a function over the features in the collection. Reduce. So map is doing the same thing to every element in a collection. A reduction or reducing a collection is aggregating things into fewer things. So for example, you can take an image collection and aggregate it. The example I gave you previously is with the median. So creating a cloud-free composite with a median reducer in every pixel is an example of a reduce operation. And so this is a temporal reduction. So imagine this is a time series and you want to make a single composite out of that time series. You can do a reduce operation, but you could also take the mean of pixels in an area here, and that is a spatial reduction. There are lots and lots and lots of reducers in Earth Engine, and you just have to see the docs to know what these are. I'll show you where those docs are in a second, but there are lots and lots of reducers. Think of a reducer as just a statistic type. So you can reduce the bands of an image. So this is a spectral reduction. So for example, you could take the sum of bands, and if you have many bands, you get one band out. So you're reducing the number of bands here. You can reduce a neighborhood. So here the input to the reducer is this little sliding window here, and this slides around, and you can compute, for example, the mean of pixels in that little window is a low-pass filtering operation, but there are also edge detection filters and so forth. So this is called reduce neighborhood, and that's how convolutions are implemented in Earth Engine. You can reduce an image collection. So again, the example here is making a median composite out of many cloudy images. So for example, these might be cloudy images, and when you compute the median, it happens in each band, in each pixel. And again, the inputs can have different resolutions and registrations and projections, and Earth Engine will take care of all that for you and give you an output image from reducing a collection. You can reduce a region. So this is a spatial reduction or a spatial aggregation. So say this is your region, this is your input image, and this is your region. And what you want is the mean of polygons inside that region. That is a spatial reduction, and that is implemented with the reduce region function. And what you get out is a dictionary with the keys. The keys in the dictionary are the band names of the image, And the output and the values in the dictionary are the output of the reducer, so the mean of pixels in that region, or the max or the min, or whatever kind of reducer you use. You can reduce regions, so this is getting the mean pixel value into all these polygons. These might come from a Google Fusion table or a shape file that you've uploaded to Earth Engine. You can upload shape files directly. And then if each row is a feature here, what you get out are more attributes. Specifically, you get an attribute for each band in the image.